In this video, we are going to talk about ANOVA test, which is being used for 3 or more population means. So let's just repeat this process, okay? So if you take a look at level of the measurement of a dependent variable, that is a continuous variable, and the level of measurement of the independent variable, that is a categorical variable that has 3 or more categorized, then we are going to use the ANOVA. The example here, you see this example for a couple of times, right? Compared to males, do females spend less time in the prison? The dependent variable is length of incarceration measured by the year 1, 2, 3, 4, 5 years. Independent variable is gender measured by male and female. So the dependent variable is a continuous variable. Independent variable is a categorical variable. The proper way we use is the t-test because the independent variable only has 2 categories. Is there any difference among officers with different races regarding the number of traffic tickets they write? The dependent variable is the number of the traffic ticket, and the independent variable is officer's race, measured by white, black, Asian, Hispanic. So there are 4 groups. So the proper test that we use here is ANOVA. Those are the one we talked about in the previous PowerPoints already. So the ANOVA is short for analysis of variance, the proper analytical technique to use when independent variable is categorical with 3 or more classes and the dependent variable is a continuous variable. Okay, so it's a hypothesis testing procedure rely on the variance. Okay, so our hypothesis test is testing that the variances across the categories is due to the true difference among those different groups based on the categories. Okay, the problem with that, or some people has a question about, well, since you are looking at analysis of the mean among different population, why don't you use a bunch of t-tests? For example, if we have 3 groups, 1, 2, 3, right? So if we have 2 groups, 1, 2, we just use a t-test. It's 1 t-test. But if we have 3 groups, we may use t-test like 1 and 2. That's a 1 t-test. 1 and 3, that's a second t-test. 1 and 3, that's the third t-test. So there are 3 t-tests, right? So why don't we just use 3 t-tests, but we use the ANOVA to analyze all the groups means in the same time? So the problem with using lots of t-tests in ANOVA or in analyze like more than 2, 3, 4, 5, 6, 7 groups is that it is going to increase the likelihood of a type 1 error. We talk about type 1 error, that is the error that we reject what we suppose not to reject. Okay, so another issues with using multiple t-tests is that the results gets messy. You can't really see the difference from a clear sight, and also the results could be really hard to interpret it. So for here, like you have 3 t-test results, each of them may have significance or not significance. It's kind of a really messy to interpret the results. And then another big reason is that we would not be able to say that we are 95% confident or 99% confident in our analysis because we're running a bunch of analysis and we can't really combine them together. Okay, so that's why we choose to use the ANOVA in this situation instead of using a bunch of t-tests. Before we actually go into the examples, we need to understand some basic concepts of ANOVA. Okay, the concept 1 is the groups, classes in the categorical independent variable. This is the one that divides the data into different sort of subsamples. And another term is called a between group variance. It's the extent to which a set of groups or classes are similar or different from one another. Okay, this is a measure of true group effect or a relationship between the IV and DV. So within group variance is is the amount of diversity that exists among the people in a single group or class. This is a measurement of random error. So the thing is, the very first one between group of variance, if it's really high, really a lot, that means, well, there is a relationship between the independent variable and dependent variable because each of the group are really different. However, if the within group of variances are really high, that basically means that the difference between the independent variable and dependent variable may be coming from um, the people within the groups. Okay, each of the groups, the subjects in the groups are kind of different from each other. That's caused the whole difference that's showing. So as you can see, the ANOVA test, we call them the F test, and it is a ratio of the amount of between group of variance and compared to the within group of variance. Okay, so it's like the between group and divided by the within group. If this F value is really high, that means the between group is high, right? So the between group is high, that means there is a relationship between the dependent variable and independent variable. If the within group variance is high, that means this one is getting small. Okay, this F test is F value is getting small. That means there is no such a difference between the groups. The difference coming from is from within the group subject. Okay, so before we do that, we will talk about the F distribution. That is another new distribution will be covered. So if you take a look at the ANOVA analysis of variance, when you see the word variance, what do you think? The variance, when we talk about in the previous PowerPoint, the variance is something like you square something, right? Now, again, if you square something, that means all the numbers, all the final numbers will be a positive number because you square it. So, similar to the chi-square, the F-test has all the values are positive values. It does not have a zero, or it may have a zero value, but it does not have a negative value. So what you see here is the F distribution. Well, it looked like a chi-square distribution, right? It really looked like a chi-square distribution. It's a positive skewed distribution starting from like a zero or less than zero, but there is no negative number and only picks one and has a long tail toward the positive side. Okay, so the non-hypothesis in the ANOVA and the alternative hypothesis in the ANOVA is a little bit different from the non-hypothesis and alternative hypothesis in the t-test. So the non-hypothesis in the ANOVA, since it has three or more than three groups, but every logic is the same, is that there is no difference between each of the groups among those groups, whatever you can say it. Okay, so if we have three groups, then the mu1 equals to mu2 equals to mu3. This literally means the population 1 or the mean of the population 1 equals to the mean of the population 2 equals to the mean of the population 3. If you have four groups, then mu1 equals to mu2 equals to mu3 equals to mu4. Okay, the alternative hypothesis in the ANOVA is very different, and you have to keep this in mind that if you have two groups, then just like a t-test, the alternative hypothesis could be mu1 larger than mu2, mu1 less than mu2, or mu1 unequal to mu2. But in ANOVA, this is not the case. In ANOVA, you can't simply write something like this, or something like mu1 larger than mu2, smaller than mu3, larger than mu4. No, that doesn't make any sense, okay? So the alternative hypothesis in the ANOVA looks like this. Some mu's are not equal to some other mu's. Okay, and this is a very important concept in the ANOVA, is that we don't say mu1 less than mu2 bigger than mu3 something. We just say some mu's are not equal to some other mu's. Okay, so the only information here is one group is significantly different from another group. The F test or F number indicates neither the number of the difference nor the specific group that stands out from the others. Okay, so the only conclusion that can be made is that one group mean is different from another. Okay, now typically what I use is this sentence: at least one group mean is significantly different from at least one another. In terms of which group is different from which other group, we will have to do some further test. But simply doing a ANOVA test based on the F value that only gives us the alternative hypothesis as at least one group mean is significantly different from at least one another. Okay, so like I said, simply doing F-test does not tell you which one is different from which other one. So the one we're going to do is we will have some post hoc tests. These are the analysis conducted where the null hypothesis is rejected. So when the null hypothesis is rejected, what do we talk about? At least one group mean is different from at least one another. Now the post hoc test will tell us like which one is different from which other one. Okay, so it allows the researchers to determine which groups are differently from which other groups. It may be from one group different from another group. Okay, or it maybe one group is different from other two groups, or one group is different from other three groups. It's all coming from the post-hoc test. It doesn't coming from the F-test itself. It doesn't coming from ANOVA, the F-test itself. Okay. So two ways, or typically or traditionally, we have two ways to run this post-hoc test. So one is we call the HSD. It's a very popular one. It compares each group to others in a series of two variable hypothesis tests. The non-hypothesis, again, the non-hypothesis logically is the same. That group means are equal. And if you can reject the non-hypothesis, that there is a significance between the groups. Okay, the same logic as we run like in the t-test. But also we have another way to analyze the when the null hypothesis is rejected. Okay, so in this way it minimizes the type 1 error, which is reject something we should not reject it, but it's very conservative. So the best way, now typically social scientists doing, is to use two of them. Okay, use the HSD and this B test to run the post hoc tests to compare the results from two of the post hoc tests and to see if they share the similar or maybe there is a difference, so we can make a conclusion. Okay, however, now in today's PowerPoints, there is we don't really talk about how to do the Turkey test or the other post hoc test. The thing is that they you can usually get those numbers, get use tables from running the statistical software such as SPSS, Data R, something like that. Now, in order to we just calculate the F test to reach our conclusion like at least which one group is significantly different from at least which other groups, we are simply using the F-test. Okay, so the 5 steps is the same. The first is state the null and alternative hypothesis. Second is identify the distribution. We talk about this is ANOVA, so we use the F distribution. Compute the degree of freedom used to find the critical value, and use a series process to compute the obtained value. And based on the critical value and obtained value, we are going to see what we do with the null hypothesis, whether we reject the null hypothesis or whether we accept the null hypothesis. The same steps as the chi-square test and the t-test. Okay, now this week let's go to some examples. The first example asks a research question, excuse me, whether attorney type, public defender, assigned counsel, or the private attorney affects the jail sentences received by the inmates. So you can see the table look like this one. The dependent variable will be the jail sentence, right? The time or how many months they gonna stay in the jail. And the independent variable will be attorney type. It has three values. One is a public defender, second is assigned counsel, and the third one is private attorney. So based on what we know is that we are going to analyze it with the ANOVA approach, right? So how to read this table? The first one is that you can see we have 5 cases in the public defender group. Now, the first person got 1 month in the jail, second person got 2 months in the jail, third person got 9 months in the jail, right? We also have 4 people in the assigned counsel. The first person got 4 months in the jail, the second person got 2 months in the jail. We also have the private attorney. Okay, we have 6 of them. The first person got 3 months in the jail, the second person got 8 months in the jail, and the third person got 10 months in the jail. Okay, that's how we read it. Now, again, like we talked about like 5 minutes ago, the research question leads to the hypothesis, and the non-hypothesis will always be the mu1 equals to mu2 equals to mu3. And you can see why there are 3, because we have 3 groups. And in a sentence, in a plain language, there is no significant difference among the 3 attorneys regarding jail sentences received by the inmates. Okay, it's just the same time, same length. So the alternative hypothesis, again, we talk about this, is very unique in the ANOVA, is some mu's are not equal to some other mu's. So put it in a way, among the 3 groups, there is at least one group is significantly different from at least one other group. We don't make a directional test or directional assumption like which one has longer time in the jail than other groups. We can't. It's just simply we can't. Okay, we just say there is at least one group is significantly different from at least one other group. Okay, so the distribution, again, the distribution we use in the F test, we just introduced the F distribution, which look like a chi-square distribution, right? The degree of freedom in the ANOVA is a little bit different from like a t-test or chi-square because a degree of freedom has 2. One is called the between group degree of freedom, DFB. That's the number of the groups minus 1. Okay, the second is within group DFW, within group degree freedom. That's the total sample size, the big sample size across all the groups minus the number of the groups. Okay, we need those 2 degree freedom to look for our critical, the F critical value, and which will be conducted in the step 3. So in this example, you can see what is the degree of freedom between. That would be the group number minus 1. We have 3 groups, so 3 minus 1, that would be 2, right? What is the within group? That would be the total sample size, that's 5 plus 9, 4 plus 6, that's a 15. 15 minus 3, 3 is a group, but the number of the groups, okay, so it's a 15 minus 3, that's 12. So we have DFB as 2, DFW as 12. Now we're going to find the critical value. This is the F distribution. Same logic, just like a chi-square. Okay, same logic. If we have the critical F value and the obtained F value is larger in these areas, then we are going to reject the null hypothesis. If the F value, obtained value, is in these areas less than the F critical value, we are going to accept the null hypothesis. It's just the same logic. So what do we do here? We have, again, this is a one tail, right? We don't have to say that, but this is just one tail. Alpha level 0.01, degree of freedom between group is 2, degree of freedom within group is 12. Now you're going to see this is a typical F table, the distribution of F distribution and how we're going to read it. So you are the DF1, which is across a row, that the DF1, this is a column, I suggest the column 1, 2, 3, right? This is a usually represents the DF between groups. Okay, so in this one, this is the one we usually suggest the DF within groups. Okay, So what do we have here is that we have alpha level 0.01. Okay, you have to look at the alpha level 0.01. You may have another F table suggest like alpha 0.05. Okay, you may have another one, but the same logic when you're going to find out the F critical. And we have degree of freedom between as a 2 and degree of freedom within as a 12. Now you have the F critical is 6.93. And again, since this is one child and only positive values in F distribution, so we don't need to look at if there is a negative number. It only has a positive number, right? So the F critical will be 6.93 for sure. So you put this on the table, not table, on in the chart, and you will see this is a one that you get the critical F value 6.93, and anything larger than 6.93 will be in the rejection area. For example, if you get a 7, you get a 70, whatever, it doesn't matter. Okay, will be the rejection area. Anything that is less than 6.93, like here, like a 5 or like a 2, 1, will be in the exception of the non-hypothesis area. The question is, what if you get the F obtained like a negative? That means there is a mistake. You have to double check it. The F obtained or the any F value is not going to be a negative. If it's a negative, that means there is a mistake in your calculation. Okay, that it's just that simple. So let's compute the obtained value. Now in the ANOVA, obtained value a little slightly complicated, but later I will simplify that for you. Okay, before we do calculation, we needed to know the symbolics or the symbols or any of the letters that represents what do they represent. Okay, so NK, that means the sample size of group K, the number of the cases in each group. Okay, the big N means the total sample size. We always use the big N means the total sample size. The XK bar means a group mean. How many groups you have, then you have how many group means. Okay, xg bar, that's the grand mean, the mean for the whole sample. So you add everything together divided by the whole sample size, you will get the grand mean, which is xg bar. Okay, the sums of squares, the SSB is the between group sum of the squares, SSW is the within group sum of the squares, and the total sum of the squares equals to SSB plus SSW. So if you add those things together, then you will get the SST. Okay, so MSB means the mean squares. Okay, MSB means the between group mean squares. MSW means within group mean squares. So if you go back to look at the definition of the F-test, you will know that what we comparing is the ratio of this one and this one. Okay, so SST, we are going to calculate the SST look like that. It looks a little bit complicated, but I'm going to simplify that. So the first part is just look like this, is that you add everything square and you add everything the sum of them together, and the second part look like here. Okay, so it's like you add everything together, then you square it. Okay, be careful like when you square it. Okay, now I will do a worksheet later in the PowerPoint, so this is just going to briefly talk about how you do this one. Okay, so the SSB, the between group, will be the part of this one whole thing will be look like this. Okay, so that's the number, sample number. What should I say? The number of the cases in the sample one, and using the mean of the sample one minus the grand mean, and number of the cases in the sample 2 multiplied by the mean of the sample 2 minus the grand mean, something like that, etc. Right? The problem is that why we use the SST and SSB, because it's a little bit hard to calculate the SSW directly. That is why we calculate the SST and the SSB, and based on the formula, SSW and SSB will equal to the SST. So SST minus SSB will be the SSW, right? Because it's so hard to calculate these things um, alone. So you calculate those two to get the SSW. So the MSB will be the SSB, the between variance divided by, what is this one? Is this a DF, degree of freedom between groups, right? The bottom is the degree of freedom between groups. And the MSW, the mean of within group, is like the within group variances, and divided by, what is this? That's a DFW, right? So the degree of freedom within groups. So it's the same. So when you're going to use that one, like we talked about before, is that the F-test is really like a ratio. What is a ratio? Ratio means you use the MSB divided by the MSW. So this is the final F obtained. It's a ratio of mean SB and the ratio divided by the mean of SW. Okay, so it looks like the formula looks a little bit different, complicated, but if you have the working sheet like this, it makes everything easier. So I usually give the student who wants to doing this by hand as a working sheet like this one. So x1, the origin number of x1, the second column is x1 square, x2 look like that. The another column is x2 square, x3 square, sum of the x1, mean of the x1, and the sum of the x1 square. Okay, similar to the x2, sum of the x2, mean of the x2, and the sum of the x2 square. Okay, then we also need this grand mean. That means you add everything together, all the numbers together, divided by the total sample size here, which is 15, right? So you put every number inside of it. It's really quick, really easy. So square one is 1, square 2 is 4, square 9 is 89, something like that. You add everything together, you get the total number of 21 divided by the sample size 5 in group 1. You will have the mean of the 1, 4.20, and you also add all the square here together, 131. So when you do everything, don't forget about calculate the grand mean, which is 5.93. Okay, so once you have everything like here, this one, then you will have everything in the formula. So take a look at the formula. Do you have this one? Sigma x1 square? Yes. Do you have this one? Sigma x2 square? Yes. Do you have this one? Sigma x3 square? Yes. Right? And we just use the x3, so these are not. So do you have the x1? Sum of the x1? Yes. Right? Sum of the x2? Yes. Sum of the x3? Yes. And that's it. Okay, and you replace those things with the numbers, and again make sure that you calculate one by one, and you will have the SST as a final 186.93. That's just for the SST. So for the SSB, so do you have the N1? Yes, that's a 5, right? Do you have the mean of the first group and the grand mean? Mean of the first group and the grand mean. Grand mean is here. Yes, right? So you do the same thing for the second group. You do the same another thing for the third group. You can make the third group like here. Okay. So you will again put those numbers into the formula and calculate the whole thing carefully, and you will get the SSB as 84.41. Now you can pause the video and use your calculator to double check it. Okay. So now you have the SST and the SSB. Where is the SSW? It's easy, just the SST minus SSB. That will be the SSW as 102.52. Right? Now you have the MSB, which is the top of the obtained F value formula. The SSB divided by the degree of freedom between groups, that is 42.21. The MSW, that's the bottom of the obtained value of F. you have the within SSW divided by the degree of freedom within groups. That'll be 8.54. Now, eventually, this is a ratio of those two values, right? It's a ratio of those MSB and MSW. You will get obtain 4.94. Thank God we got it. Okay, 4.94. So where is this 4.94? So the critical F value is 6.93. Anything larger than 6.93 is going to be the rejection area. However, what we have is 4.94. We are in this area. So what do we do? Quite easy. We cannot reject the null hypothesis, right? So we are going to accept the null hypothesis. So simultaneously we reject on alternative hypothesis. So the conclusion in plain language is there is no significant difference among three attorney types regarding the jail sentences received by the inmates. Okay, it's just that simple. And in because there is no significant difference, do we continue to see which group is different from another group? No. Okay, because our alternative hypothesis is at least one group is different from at least another. Then, but we reject an alternative hypothesis, right? We accept the null hypothesis. That means uh, all the three population means are statistically same. Okay, so there is no difference. If there is no difference, we don't have to go further to see, oh, which one is different from another. But they don't have different. Why are you going moving to the next stage, right? So we stop here. There's nothing we can do in the next because we accept the null hypothesis. So let's take a look at another example since we already know the whole process and the calculation stuff like that. So we are going to move a little bit fast, okay? The second question is whether there are significant regional differences in handgun murder rate. Okay, so I guess these are from, let's say these are from different parts of the United States. We have Northeast, Midwest, South, and West, and these numbers represent different states. And their handgun murder rates in different areas. Northeast, what are the states in the Northeast? I don't know. New York State, maybe. Maybe Vermont. I don't know. And south, you may have some states like what, Texas, something like that. Okay. West, you may have like California, something like that. Okay. Anyway, I don't care. Okay. But the thing is, you can see we have what, 1, 2, 3, 4 groups, and the murder rate is or handgun murder rate is our dependent variable. The dependent variable measured by those numbers, right? It's a rate, it's a numbers. So it's a continuous variable. And our independent variable is the regions across the US. So 4 different regions. So we are going to use ANOVA. Okay. Again, we're moving a little bit fast. Is that null hypothesis is mu1 equals to mu2 equals to mu3 equals to mu4. Here you can see we have 4 groups, so we have to have 4 mu's. Okay, there is no significant difference among different places regarding the handgun murder rates, and the alternative hypothesis will be the same whether you have 5 groups, 6 groups, 100 groups in the ANOVA. The alternative hypothesis is still going to be some mu's are not equal to some other mu's. Okay, so in a sentence, it's among 4 groups. There is at least one group is significantly different from at least one another group. Okay. The distribution, again, we use the F test or F distribution. The degree of freedom, remember, we have the DFB and DFW. So the DFB is the group of the number of the groups, 1, 2, 3, 4, 4 minus 1, 3. The within group degree of freedom will be the total sample size, 5 plus 5 plus 7 plus 6. Minus the group number 1, 2, 3, 4, so that's 19. So 3 and 19, that's our answer for the degree of freedom. So again, it's a one tail. We don't have to say because it's a one tail. Alpha level 0.05, degree of freedom between 3, degree of freedom within as a 19, and we put this pull out this table, and particularly pay attention that this table is a little bit different from the previous example because this is a table showing alpha level at 0.05. Okay, the previous one showing the alpha level at 0.1. So you have degree freedom of 3, the DFB 3, DFW 19. What do you have? 3.13. Okay, and it's a positive. It has to be a positive. So you mark it. The critical F value will be 3.13 here, and rejection area will be here. Anything larger than the 3.13 will be we will make the decision to reject the null hypothesis, like 4, 5, 7. Okay, anything smaller than 3.13 will be accept the null hypothesis, such as 2, 1. Anything negative means like you made some mistakes and recalculate the whole f obtained value. Okay, so again, we use this working sheet to compute the obtained value. Compared to the previous one, we just add one more group as the group 4. Okay, I'm not going to spend more time on this one. It's just you can pause the video here and try to write down or fill the whole table by yourself and compare to the answers here. Okay, now you have everything that in the later formula we need, like a sigma or sum of the x1 and the sum of the x1 square and the mean of the x1 and the grand mean. You will have every number here. The similar applies to the x2 groups and apply to the x3 group and the x4 groups. Okay, again, I'm not going to repeat it there. You just mimic the previous formula and replace all the symbols, letters with the numbers that we did in our previous working sheet here. Okay, then carefully run the calculation. You will have the SST as 29.43. And again, you mimic the one we did before. Okay, using the working sheet and carefully replace those letters, formulas, and with your numbers in the working sheet and carefully calculate. You will have the SSB as 14.58. And again, we can calculate SSW directly, so we calculate SST and minus the SSB in order to get the SSW, the within group variances. So we will have the SSW here in this example is 14.85. Then everything is easy, right? The mean SB will be the SSB divided by the degree of freedom between, that's 4.86. Mean of SW will be the SSW divided by the degree of freedom within groups, that would be 0.78. And our obtained F value is just a ratio of 2, right? The ratio of the mean of SB and the mean of SW, that would be 6.23 is our final answer. Okay, so again, make a decision here. So F critical 3.13, anything larger than 3.13 will be the rejection area. Anything less than 3.13 will be the exception area. So what we have is 6.23. Wow, nice. So what does this mean? So this means we are going to, easy, first of all, we are going to reject the noun, right? We are going to reject noun and we are going to accept the alternative hypothesis. What is the alternative hypothesis? Some population means are different from some other population means. Remember, there is no particular which group is different from which group. It's just some of them are significantly different from some other. So the conclusion is there is a significant difference among different places regarding the handgun murder. Okay, so among 4 groups, Northeast, Midwest, South, and West, there is at least one group is significantly different from at least one or one other groups. We still cannot know which one is different from the other one because, like I mentioned 25 minutes ago, the simple ANOVA test like this give you an F value that only give you an answer about whether there is at least one group is different from at least one other group. It does not give you the answer like if there is a significant difference, then which two are significantly different, right? It doesn't give you that answer. So if you want to see that answer, you have to go through the post-hoc test. Okay, so this is just a repeat slides in the previous for similar to the previous slides is that we have two of the ways that to do the post-hoc test. So and in typically like social sciences is just using two of them and to see if they are giving the same information. Okay, if they're giving the same information, that's great. If their information is different from each other, then they have to decide which one makes more sense. Okay. But the thing is that we are not going to cover the post-hoc test in this PowerPoints. This is the one usually conducted by computational software or statistical software like SPSS data or HLM, something like that. So we're just going to stop here. That's it for the ANOVA test.